Hi, everyone. We are hopeful to have John Sorce from MIT today, who's going to talk about information theory in the semiclassical.
Thanks. Okay, great. As always, it's really fun to be at UChicago. I'm here through the end of day on Wednesday, so I hope I get to interact with a lot of you. The work I'm going to be talking about today is something that I've been developing over the past few years, which has to do with the information theory of semiclassical black holes. And in particular, I'm going to talk about two papers. I guess you can see, well, there you can see the citation, sort of. Two papers, one that I wrote last year with Chris Akers and one that I wrote just a month or two ago. Actually, the paper with Chris was written before the last time I gave a talk at UChicago, but I didn't talk about it, and there have been developments, so I figured it would be fair game. This is a talk about quantum gravity. I know the audience is quite broad. I hope, as always, that you'll feel comfortable interrupting me to ask questions and slow me down. So, as I've said, this is a talk about quantum gravity, and like most talks about quantum gravity, it starts with black hole thermodynamics. So this is an invention of the 1970s, during which time it was realized that black holes in general relativity behave in many ways like thermodynamic objects. So this starts with the observation due to Christodoulou and Hawking that when you perturb a black hole, its area tends to increase, much like the entropy of an ordinary matter system. Turns out this isn't just an accident, because Bekenstein shows that if you throw matter with a certain amount of entropy into a black hole, then the area of the black hole increases by a compensating amount. So a black hole really does behave like an object with entropy proportional to its horizon area. This is bolstered by the observation that black hole perturbations satisfy a first law. The change in energy is proportional to the change in area. And moreover, when you include quantum effects, black holes radiate like black bodies. So put together, these are a bunch of observations that tell us that black holes seem to behave thermally. This is an observation that is in need of an explanation, some kind of framework to explain why it happens. And the simplest guess, and one that's motivated a lot of research in quantum gravity in the past 50 years, is that the same mechanism that causes matter to behave thermodynamically should also be what causes black holes to behave thermodynamically. In other words, you can guess that there's a fundamental underlying statistical principle. So this is a guess that in the theory of quantum gravity, black holes should be complex statistical systems with a number of microstates set by the entropy, which is proportional to the horizon area. This is a prediction of classical general relativity about theories of quantum gravity. So if you have a theory of quantum gravity where you can compute things, you can go and try to check this. So to my mind, there are three settings in which this has been explored very robustly. Maybe the most famous of them being the counting of supersymmetric degeneracies in string theory for extremal black holes. There's also a pretty famous setting in low-dimensional holography where one can verify this formula just by using essentially the conformal bootstrap in 2 dimensions. And then more recently, there's been some work in frameworks for quantum gravity that are built around the gravitational path integral. So in all three of these settings, one can actually verify you have a theory of quantum gravity in which a black hole is an object with a number of microstates set by the exponential of the area. One thing I want to point out is that this gives very strong evidence that one should generally believe this guess. But an interesting feature of these calculations is that they're all very different. You have to, depending on the particular theory of quantum gravity that you're studying, you have to do something different in order to study sort of the microstate structure of black holes. And to some extent, that's unavoidable, but I think it makes it worth asking, how much of this guess can we understand without recourse to a specific theory of quantum gravity? This is useful in part because it helps us unify our understanding of all of these examples, and also in part because we don't yet have a controllable theory of quantum gravity with positive cosmological constant. So it's worth pushing as far as we can towards understanding this guess without needing to specify microscopic details.
Also, this is very closely tied to Susie in almost every case.
Indefinitely in this case, it is.
Also, the gravitational path integral.
Well, yes and no. Okay, in the ADS, so definitely in this first case, there's Susie. In the second case, there's Susie in these settings where you're using the path integral to compute the supersymmetric index. But there are also cases, there's this interesting paper by Vijay Balasubramanian, Martin Javier Magan, Martin Sacieta, and Albion Lawrence, which talks about essentially a a purely classical GR path integral supplemented by matter shells, which reproduces some effective rank of a black hole density matrix that scales like e to the area. So that doesn't require SUSY. It's less robust in some way because it involves some semi-classical approximation and there's no like supersymmetric localization to make everything very exact, but I think it goes beyond SUSY.
It also requires some dodgy assumptions about ensemble everything.
Well, of course, it requires some assumptions about chaotic dynamics and coarse graining and, you know, SUSY plus some other settings where SUSY can be relaxed, but in a dodgy way, let's say.
And even point two, the speculation doesn't exist without SUSY.
Oh, that the theory doesn't exist without SUSY?
There's no AES3 CFT theory.
Yeah, so that might be true. At the very least, the CFT calculation is, at a basic level, it's Cardy's formula, and then it's Cardy's formula supplemented by this work by Hartman, Keller, and Stoica using a sparse light spectrum. Okay. So in order to talk about how much we can get about this guess without knowing a specific quantum theory of gravity, I want to draw your attention to sort of a missing link in the analogy between matter and black holes. So if you think about the history of thermodynamics, it starts with this empirical observation. Is there a laser pointer? Maybe not. It starts with this empirical observation that matter behaves thermodynamic principles. Boltzmann and Gibbs invent classical statistical mechanics in order to explain that. And then it's realized that there are fundamental inconsistencies in the theory of stat mech, and quantum mechanics is invented to resolve them. On the other hand, when black hole thermodynamics was discovered, we already knew about quantum mechanics and went immediately to trying to explain black hole thermodynamics using quantum gravity. This is something that's been very successful, but I think it's worth asking, especially because of the difficulty of working with specific theories of quantum gravity, if there's something that sits in the middle and plays the same role as classical stat mech in the matter setting. And I'm going to be telling you what the proposal is for that question mark. Okay. So here's the outline of the talk. I'm going to start just by talking about the relationship between classical and quantum statistical mechanics. In a sense, it's undergrad material, but I'm going to say it in a way that you probably haven't seen before and that I think will set us up to understand the rest of the talk. Then I'm going to talk about the thing that fills in this question mark, which is the so-called cross-product entropy. Let me ask, has the Kavanaugh Center had a talk about the cross-product before?
I think so.
You think so? But maybe, I think so means that probably not everyone's going to remember it. So this is something that's been developed over the past few years. It's a technology for studying entropy for semiclassical black holes without needing to know the details of a microscopic realization. This isn't a talk about the cross product, so I'm not going to spend a huge amount of time on it, but I will try to give you an introduction to my perspective on what this technology is and why it works. Then I'll tell you the main meat of the talk, which is a paper I wrote with Chris Akers last year, where we showed that this framework actually does have an information-theoretic interpretation, and it gives you a way to do what I'm going to call relative state counting in the semiclassical limit. Finally, if we have time, I'll tell you about my most recent paper, which I think gives us some clues as to how all of this technology should be embedded in a true theory of quantum gravity. All right. So let's start by talking about classical stat mech. Classical stat mech is in particular classical mechanics, so we're in phase space, and states are points in phase space. Ensembles are just probability distributions on phase space. There's an inherent ambiguity in any probability distribution on phase space, which comes from the fact that phase space is dimensional. So the measure on phase space isn't preferred. dxdp is just as good as 5dxdp or any other constant times dxdp. Essentially what that means is that you don't really have probability distributions, you have something like equivalence classes of probability distributions up to scaling. And that's an ambiguity you have to build into your calculations of physical quantities. Now, if you have quantum mechanics, then h bar provides units, a fundamental constant with units of action that you can use to canonically normalize this measure. But if you don't know quantum mechanics and you're just working in the classical theory, you have to deal with this ambiguity. Nevertheless, you can proceed as Boltzmann did and define the entropy of an ensemble as minus integral p log p, and you just study what happens to this quantity when you abuse your fundamental ambiguity, and you find that the ambiguity in the measure on phase space leads to an additive ambiguity in the entropy. What that means is that at the classical level, entropy isn't well defined. Total entropy doesn't make sense in classical stat mech, but entropy difference is, because the only ambiguity we have is this overall additive constant. The great success of classical statistical mechanics is realizing that this is actually enough to explain thermodynamics. You don't need to know the entropy, the absolute entropy of a piece of matter in order to explain why a system moves from a lower entropy configuration to a higher entropy one. All you need to know is what it means for one system to have more entropy than another. So we're going to see how this is analogized in the theory of black holes, but first, to set up for the end of the talk, let me say a few words about how this story gets fixed up when you add quantum mechanics. So when you have quantum mechanics, you're in Hilbert space, not phase space. That means you have no dimensional ambiguity. A pure state is a vector in Hilbert space, an ensemble is a density operator in Hilbert space, and you have a canonical normalization for your states provided by the trace on Hilbert space. That means that you can use von Neumann's famous formula for entropy, minus trace rho log rho, and define an absolute entropy of a quantum state without this overall ambiguity that you have in the classical setting. In particular, when you study a microcanonical state, which is a state that's uniformly distributed over some subspace of Hilbert space, so it's a density matrix that's just proportional to some projection operator, then you find that the entropy is just log of the dimension of that subspace. This is what we mean when we say entropy counts states. We mean the entropy of a microcanonical state tells us something about the number of microstates over which that state is distributed. And this is more or less what we think black hole entropy is getting at. So let me just say one word about how the classical picture emerges from the quantum one. Well, very roughly speaking, in a canonically quantized system, the Hilbert space trace goes over in a phase space picture to the integral with respect to dx dp over h bar. What that means is that when you take the classical limit of h bar to 0, this expression diverges. That makes all entropies in classical mechanics formally infinite, because they're all sort of proportional to 1 over h bar. But this doesn't stop us from doing StatMech, because we can just renormalize away the divergence. We're going to try to do something similar now for black holes. This is everything I want to say about classical and quantum StatMech. Any questions? So now I'll tell you about this cross product, which is a tool that you can use to study entropy in semiclassical quantum gravity. So the key technique or the key framework that we're going to be using is the framework of local algebras. So let me say what I mean by that. I'm from a community where when we want to describe quantum subsystems, we describe them using an algebra of operators. And the way that this works is very simple. So if you think, for example, on the left picture here, I've drawn a lattice system where typically you would describe subsystems of a lattice by specifying some subset of the lattice sites. And on the lattice, you would assign some Hilbert space factor, HA, to a particular subset of lattice sites, and a different Hilbert space factor, HB, to a different subset of sites. That's sort of a Schrodinger picture, way of talking about a division of a quantum system into subsystems. But there's equally a Heisenberg picture, which is just as good, where you talk about the subsystem by specifying the set of operators that act non-trivially on that subsystem. That's what this notation means here. The set of all bounded operators acting on one side and acting trivially on all of the other sites. The reason that I prefer this Heisenberg picture for talking about subsystems is because it works even in the continuum. In continuum quantum field theory, you might want to talk about a subsystem describing, say, the degrees of freedom inside a causal diamond. And that's something that doesn't admit a Hilbert space factorization unless you put in a UV regulator, which is something that you can do for certain computations, but for other computations, it can end up being more confusing than it's worth. Nevertheless, you can always talk about the algebra of fields localized in a particular region. Now, I've written up here that I'm going to describe a general quantum system by a collection of operators arranged into what's called a von Neumann algebra. Doesn't matter for this talk what a von Neumann algebra is. It's a collection of operators satisfying some nice conditions that makes them useful for describing physical systems. So anytime you see the words von Neumann algebra, you can just think physical subsystem. Now, once we have a way of describing subsystems using these algebras, we can talk about things like density matrices and associated entropies. So let's talk about the density matrix associated with a subsystem in this general framework. Well, what you have is a state, psi, which is like some global state of a system, say quantum field theory, and you want a density operator in a particular algebra describing a subsystem. So maybe you can always have in mind this example where my subsystem is a causal diamond. Let's say I have some global state psi, whose restriction to this causal diamond I want to study. So, well, what do I mean by a density matrix? I just mean some positive operator in the algebra describing the subsystem that reproduces all of the right expectation values via the standard formula for density matrices. There's a problem in trying to do this in continuum quantum theories, which is that you can end up studying algebras that don't have any density operators. It's actually typical in quantum field theory that the algebras describing local subsystems don't contain any operators with finite trace. All of the operators in them are going to have some divergent trace, and you can't even talk about this formula. So, in a sense, that makes it sound like we're dead in the water as far as talking about entropy. But as physicists, we know what to do when something diverges. We try to renormalize it and get something meaningful and finite. And if you think about the analogy with classical stat mech, that's actually what happened when you passed from quantum to classical statistical mechanics. There was some measure on phase space inherited from the true quantum theory that looked like it was infinite, but there were a set of renormalized measures on phase space that you could use to do classical statistical mechanics. So we might imagine that a similar thing happens when we try to study something like entropy in quantum field theory. Quantum field theory is like a low energy approximation to quantum gravity. And maybe what's happening is that this trace in quantum field theory is really proportional to 1 over the scale of quantum gravity times something renormalized that we could actually compute with. And if we can figure out how to strip off this divergence, then we would still be able to study statistics of quantum gravity purely in the limit of quantum field theory. So there's an extremely elegant technology for doing this. And it's a technology that is very familiar to mathematicians and also very familiar to information theorists. We have some object that we're looking for, which is something that renormalizes our notion of the trace. One way that you can find such a thing is just by writing down a list of axioms that this renormalized thing should satisfy and trying to see if you can find something that satisfies those axioms. So mathematicians have done this, although they weren't thinking in the terms of renormalization. And they've defined an abstract trace, something that plays the role of the Hilbert space trace, appropriately renormalized, as a map from your algebra to the complex numbers that satisfies the 2 basic properties of a trace: it's linear and cyclic. Now, this is sort of not enough axioms to actually encode what we mean by some renormalized object that strips off the divergences. There are a lot of pathological things that just have these 2 properties. So typically when we study them, we impose 3 other sort of physical niceness conditions. It's not going to be important for this talk that you know what those are, but I've listed them just for sort of completeness. We impose well-behavedness properties: faithful, normal, and semi-finite. We call anything with those 3 properties a renormalized trace. You can look at this review article for details on what these 3 properties are and how you should actually think about them in physics. But basically, it's a non-degeneracy criterion, a continuity criterion, and a completeness criterion. You don't want your trace to sort of kill real states in the theory. You want your trace to be continuous, and you want it to be finite on sufficiently many objects. So there are facts about the existence of these objects that fall under the name of what's called the type classification of von Neumann algebras. And it's been known since, I guess, the 70s that, unfortunately, quantum field algebras, things like this that show up in quantum field theory, typically admit no renormalized trace. They're called type 3 algebras. If you ever are looking at the archive and you see the words type 3 show up in an abstract, it's jargon for this. It's jargon for an algebra that admits no way to consistently renormalize all of your entropies. Okay? But there was a very beautiful observation made by Edward Witten in 2021, and then elaborated by Witten and collaborators, which is that there exist algebras that don't describe subsystems in quantum field theory, but rather they describe subsystems in perturbative quantum gravity. So quantum field theory coupled to gravitational fluctuations. And these algebras actually aren't of this sick type 3, they possess a renormalized trace, and they possess a renormalized trace that is unique up to scaling. That uniqueness means you can actually use this to do physics. Something with these properties, a renormalized trace that is unique up to scaling, is called a type 3 factor. I should comment by way of history and also maybe a little bit of self-promotion that these two papers showed how these algebras show up in symmetric settings, static killing horizons in perturbative quantum gravity. And in this paper with Christian Jensen and Anthony Speranza, we generalized it to the case of no symmetry. So this is sort of an abstract claim that there are these algebras that show up describing subsystems in quantum gravity, where one has a renormalized notion of trace and therefore a renormalized notion of entropy. Let me tell you a little bit more about the explicit setting where this shows up. So we start with a Schwarzschild black hole, and we start with the algebra of quantum fields in a single black hole exterior. So this is the Penrose diagram I've drawn here. And what we want to do is we want to study perturbative quantum gravity, which means we need to turn on metric fluctuations and quantize them. This is a very difficult thing to do. A lot of things happen when the metric starts fluctuating, but I can sort of divide the fluctuations into two classes. There are local fluctuations of the metric, and these are really just sort of fluctuations of a local quantum field theory. It's, the linearized graviton fluctuations. That's part of the story when you turn on perturbative quantum gravity. But another thing that happens is that the asymptotics of the spacetime can fluctuate. In particular, the mass of the black hole can change. A lot more can change, its momentum, its angular momentum, and so on. But in particular, the mass of the black hole can change, and the mass of the black hole can possess a wave function because it's now a quantum observable. So what we do when we study this cross product is we say, well, we're going to be very crude, and we're not going to try to study the full space of gravitational fluctuations around Schwarzschild. We're just going to study mass fluctuations and appropriately quantize them. So what we do is we add a Hilbert space, L2 of delta m, which is just square integrable wave functions for the mass fluctuation. And we only study mass fluctuations that are suppressed at the scale of quantum gravity. So we add this Hilbert space, we get an associated algebra, and you might think that the algebra of operators describing the corresponding gravity subsystem is just this tensor product here. The algebra of the QFT, tensor that algebra acting on the mass degrees of freedom. But that's not true, because in quantum gravity, the matter degrees of freedom and the space-time degrees of freedom are not independent of one another. They talk to each other via Einstein's equations. And if you want to actually study perturbative quantum gravity, you have to impose Einstein's equations. One way to do this is to impose Einstein's equations at the level of the states. This can be very complicated. It's some gauge fixing procedure where you need to introduce some complicated machinery. But at the level of the algebras, there's a very simple thing you can do, which is realize that what you want is to set the Hamiltonian operator of the quantum field theory equal to the mass fluctuation operator in quantum gravity. That's one component of Einstein's equations. And so what you do is you just say, I'm going to restrict my attention to only those semiclassical operators that commute with this thing that I want to set to zero in the quantum gravity theory. And that defines some new algebra A, which is an algebra of semiclassical observables. This is probably I don't know, this might be one thing that is a little bit conceptually tricky. Any questions about this before I move on?
So is this just linearized gravity then?
It's just linearized. Well, okay, it's a little bit tricky. It's not just linearized gravity. In some sense it is, but the constraints are quadratic. So it's linearized gravitons, but there's a fact about solutions to Einstein's equations, which is that there exist solutions to the linearized graviton equations of motion that don't actually embed into nonlinear solutions of Einstein's equations. And imposing this constraint basically cuts those out. So it says it's a constraint on the theory, which turns into a constraint on the Hilbert space of linearized gravitons. But the coupling between the gravitons and the metric is at a higher order. So you need to impose it on the linearized theory. It's actually quite subtle. But yes, you should think of the gravitons as just being linearized, but subject to a constraint that is inherited from the full theory.
And how is HQFT defined too?
HQFT is, well, we're in Schwarzschild, so it's the integral of, T00 on a T=0 slice, where 0 is Schwarzschild time.
I think what about regulation, how you regularize this, or,
The HQFT.
yeah,
Why do you need to regularize it?
not just the vacuum energy itself.
Oh, yeah, okay, good. So, it's something I wasn't planning on saying, but it's a good question. So, a stress tensor in quantum theory needs to be renormalized. We are in a very symmetric background in which there is a preferred equilibrium state, which is the Hartle-Hawking state. And you can renormalize the stress tensor by subtracting off the background energy of the Hartle-Hawking state.
That's a signal.
Yeah, that's something I wasn't gonna say. I mean, really, it should sort of be like delta HQFT equals delta M, where you're sort of doing fluctuations around the equilibrium state, and you're doing fluctuations around the equilibrium mass.
Is there a canonical momentum constraint that you also need to impose? Is there like a second?
Yeah, I haven't thought about this in a part of it in a while. I think because I'm only looking at the Hilbert space of mass fluctuations, this is sort of all that shows up in that sector. But if I were to allow other asymptotic charges of the space-time fluctuate, I would need to impose additional constraints.
You would presumably need to equate the momentum in the quantum field theory to the momentum of the black hole. So for instance, if you had some momentum of something colliding with the black hole would start moving. And
Absolutely. Yeah, so you might want to say that what I'm considering is like some S-wave sector of fluctuations where the only thing that changes is the black hole mass.
Yeah.
Same thing would happen if the black hole started spinning, or if it became, if it stopped being stationary even and started wobbling in crazy ways out of infinity. Okay, so this is a set of operators that describes a particular subsector of gravitational fluctuations around Schwarzschild. And the really cool thing is that this kind of algebraic construction was studied in the mathematics literature by Takasaki in 1973. And he actually wrote down an equation exactly like this one, but it wasn't specifically, A QFT and A mass like each QFT, but it was an equation that looked like this. It was a tensor product subject to a constraint. And he called such a thing a crossed product. I don't know why he called it a crossed product. It has some connection to semi-direct products of groups or something. But he proved that anything with this structure has a unique family of renormalized traces. It's one of these so-called type 2 factors. And in fact, he even wrote down a formula for what the renormalized trace is, and it's something you can compute with. So I wasn't going to write it down, but because we're pretty good on time, maybe let me just write down the formula so you can see how easy it is to compute with. So we have this Hilbert space of wave functions that describes the fluctuations of the mass. This is like a quantum mechanical Hilbert space. So it has a canonical variable, which is the mass fluctuation operator. And it also has a conjugate variable, which I'm going to call theta, right? And the formula for the renormalized trace of one of my cross product operators is just a particular expectation value. And I'll write it down and then I'll tell you what it is. I might get a sign wrong somewhere because I didn't check this formula before writing it. Okay. So all you have to do is take the operator you want to take a trace of, dress it up a little bit by something that depends on the mass fluctuation operator, and then take the expectation value in a particular tensor product state. On the QFT, you act with the equilibrium state of the black hole. It's the so-called Hartle-Hawking state. And on the extra space, you act with sort of the zero momentum eigenstate, the zero eigenstate with respect to this conjugate variable. The reason I wrote down this formula is because while it's sort of conceptually difficult to get here, it's extremely easy to compute with. You could give a talented undergrad some calculation to do with this formula, and they could do everything with just single particle quantum mechanics. And you can use this formula to compute things like density matrices and entropies. And it's not the main point of this talk, so I'll just tell you what the result is. But in particular, you can take states that are just a simple QFT state, arbitrarily chosen, and a simple wave function for the mass fluctuation of the black hole, arbitrarily chosen. And you can use these formulas, essentially, trace rho A equals expectation value of A, to find a density matrix corresponding to this state and compute its entropy. And there's a calculation that has been done, and it gives a concrete formula. Now, this formula I'm flashing to show you how simple it is. I don't expect anyone to parse this formula because I haven't told you what a lot of the ingredients are. But at the very least, you can see that it's relatively simple. It involves a relative entropy, which is an information-theoretic quantity. It involves the black hole temperature. It involves the expectation value of the mass fluctuation. It involves some classical entropy of the mass wave function. And it involves some constant. And that constant, crucially, can never be fixed by this analysis because we're in this setting where we have an overall ambiguity in our choice of trace, which leads to an overall additive ambiguity in our choice of entropy. Right? And one reason people got really excited about this formula is that if you start trying to compute with it in particular examples, you find an entropy that is consistent with the Bekenstein-Hawking formula, area over 4G plus matter entropy plus mass entropy, with the caveat that in this formula, we're only ever capturing differences of Bekenstein-Hawking entropy and not the absolute Bekenstein-Hawking entropies.
What's S mass?
Oh, it's this term. It's the entropy of the wave function of the mass. It's like the log correction to entropy if you think about something computed in, say, supergravity. There's this extra correction to the entropy that comes from the mass being spread out over various states.
So for this to be sort of nice as you try to send h bar to 0, wouldn't you want to take the first term on the right-hand side over to the left-hand side?
This over to here.
Yeah.
This is bad when you take h bar to 0 because of UV divergences in the QFT. And this is bad when you take G Newton to 0.
Yeah.
So the typical sort of story that people tell is they say that these first two terms combined should be sensible or should be well-defined. I don't necessarily know if that's true. I don't want to commit to that in all settings. It's just sort of each of these terms comes out if you do a regulated version of this calculation. I think actually it is the left that you should expect to be finite and well-defined because this formula is UV finite and well-defined with no regulator. So this was the state of the art as of April of last year. A structure that lets you compute entropy difference in semiclassical gravity. But there was, I think, an open question, which is, what does this mean? In some sense, it's a very rigid mathematical structure, so there wasn't anything else you could have done. But it's also a very formal structure. So you've computed some entropy differences in some abstract language, but it's not clear that they have an information-theoretic interpretation. It's not clear that they teach you something about black holes. So the thing I want to ask is if this formalism can be used to intuit something like classical statistical mechanics, to intuit that certain black hole configurations have more or fewer states than others, even if the number of states is formally infinite. Okay? And the rest of this talk, I'll be telling you that the answer to that question is yes. So this is the paper I wrote with Chris last year. So the first thing we did was we restricted our attention to microcanonical density matrices in this setup. As I said towards the beginning of the talk, entropy is only expected to be a quantity that counts states when you're in a microcanonical ensemble. Otherwise, it's some more coarse-grained measure of the information in an ensemble. So in this particular setting where we're talking about sort of semi-classical operators, a microcanonical mass density matrix is just something that acts as the identity in our QFT degrees of freedom and that projects onto a particular window of the black hole mass fluctuation. And if you compute the entropy of such a thing with respect to one of these renormalized traces, you get an answer that I don't think will surprise anyone, which is you get log of trace of the projection. Now, if I hadn't renormalized this trace, if instead of this tau, I just had the Hilbert space trace, well, then I would be getting log of the rank of the projection, which is the same thing as log of the dimension of the space over which this microcanonical state is distributed. Now, in the setting that we're talking about, all of these projections actually have infinite rank. That's one of the reasons that we needed to renormalize. So this is assigning some sort of effective Hilbert space dimension to our microcanonical state. Of course, it's ambiguous because of this scale ambiguity in tau. So the only thing that we should really consider are entropy differences, equivalently the logarithm of the ratio of the traces of two projections. Now I'll tell you what this means in sort of an operational sense, what this means in terms of understanding the microstructure of black holes. So the first theorem we're going to use is a theorem about type 2 factors proved by Murray and von Neumann. I'm going to say this theorem a few different ways because I think it might sort of like, take a second or two to sink in. So the statement is about what happens when you have two projections with the same renormalized trace. So that's like this setting where we have equal entropies here. So the statement is that you have equal entropies if and only if you can do this. So this boxed set of equations says that there exists some isometry in your algebra that you can use to conjugate one projector to the other and back. Another way of saying this that might
Sorry,
be
V dagger is V inverse?
it's an isometry, so it's V is actually not invertible because it may not be unitary.
Uh-huh.
V, it's literally dagger. V is something that acts on Hilbert space. So V is a partial isometry. So actually what you have is the following. V dagger V equals Q. V dagger equals P.
Uh-huh.
Okay. It's sort of, it takes the stuff Q is supported on, maps it to the stuff P is supported on, and kills everything else. So actually, let me write that. These are projectors, they're microcanonical states. They have some support in Hilbert space. HP and HQ are sort of the subspaces where these things are supported. And this boxed equation is like saying that V takes you from HQ to HP, and V dagger takes you from HP to HQ. Okay, so let's read this second bullet point for a second. This theorem, if you think about it in physical terms, says entropies of microcanonical states are equal if and only if the supports are isomorphic via an isomorphism contained in the algebra. Let me hide this third bullet point for a second while I talk about this. So this took a little bit of time for me to wrap my head around when we were first thinking about this and its physical implications. But I think that it actually shouldn't surprise you as the right way of talking about what it means for two microcanonical states to have the same number of microstates. The number of microstates in each one is infinite. There's no way we can actually compare infinity to infinity, except by saying, well, is there or is there not some map that relates these two infinities? If there is a map that relates these two infinities, we can say that it's the same amount of infinity. If there's no map relating them, then we say that infinities are fundamentally different.
But why is it important that the map is in the algebra?
That's the rest of the talk. Okay, so it's important that the map is in the algebra at a mathematical level. We'll talk about why it's important at a physical level in a moment. At a mathematical level, it's important because if you don't put in that restriction, then any two projectors are going to have some isometry relating them. This is because any two infinite dimensional Hilbert spaces can be mapped to one another via some sort of Hilbert hotel thing where you shove all of the infinities somewhere else. Okay? So at a mathematical level, the statement is that the entropies of microcanonical black holes are equal if and only if there exists a physical gauge invariant operator that maps their supports. And I'll tell you what I think this has to do with quantum gravity in a few slides, but let me first just give you a slide that tells you what happens when the entropies are unequal. So here's the general statement, at least it's compact to write, although it might take a minute or two to unpack. What does it mean if the entropy difference is positive? So this is a setting where this microcanonical space, HK1, is bigger in entropy than this microcanonical space, HK2. Well, how do I say that a certain microcanonical infinity is bigger than another microcanonical infinity? I ask, how much do I need to add to the smaller microcanonical infinity to get to the bigger one? So that's what this formula means. It says that if you take the smaller microcanonical state and you tack on a finite number of degrees of freedom, eventually you're going to be able to embed the bigger one inside of it. And the number of degrees of freedom that you need to tack on to do this is related to this entropy difference. So that's a theorem.
But the entropy difference does not have to take value in log of integers.
It doesn't, which is why there's this bigger than or equal to here, all right? You need at least e to the entropy difference in order to be able to do this embedding. Did you ever like, when you were taking the SATs or whatever, they would ask you these questions of like, how many eggs do you need? And the answer was 3.5 eggs, but the answer was 4 eggs, because you can't have 3.5 eggs. Kind of the same thing. You know, in principle, you only need 3.5, a Q 3.5 did. But really you need a 4-dimensional space because they only come in integer quantities. Okay. Key phrase, the smaller space can be made to contain the bigger one if and only if you attach an auxiliary space with dimension at least as big as the exponential of the entropy difference. Okay,
But the entropy, but coming back to this question, entropy differences, I mean, in general, we should think they can be any real number.
they could in fact be infinite, so this only applies if they're finite, right? But yeah, they could be any real number, including positive or negative infinity. This is the correct formulation for when the entropy difference is positive. If the entropy difference were negative, then you would flip the role of K1 and K2. So this is what I called relative state counting for semiclassical black holes. It's sort of an index of infinity that tells you how much bigger one microcanonical ensemble is than another. But this is still a little bit formal, and it was still a little bit confusing for me. In particular, Clay asked this question, you know, what's with this restriction that we're dealing only with isometries that are in the algebra? So I want to tell you what I think is happening there, and an analogy that you can realize quite explicitly using classical and quantum stat mech. All right. So the fundamental statement that needs some sort of interpretation is that the entropy difference of two states is 0 if and only if their supports are related by an isometry in the algebra. And we want to understand where this restriction comes from. Well, the idea is that we're dealing with a semiclassical theory. And the semiclassical theory in principle is going to have a bunch of junk that isn't really there from the quantum theory, right? It's sort of like how if you go to the lattice, you end up with a bunch of junk at high energies that doesn't really survive in the continuum. So everything that's really going on in the semiclassical theory, everything that, you know, shows up in our analysis should be an avatar of the true underlying quantum gravity theory in the semiclassical limit. So what I think is going on is that a unitary operator acting on the underlying quantum gravity Hilbert space becomes one of these isometries in the algebra in the semiclassical limit. If we hadn't made that restriction, we would not expect those isometries to arise as consistent limits of the underlying theory. So I can actually show you very explicitly how this happens, not in a theory of quantum gravity, that's work in progress, but in a much simpler thing, which is the classical limit of the simple harmonic oscillator. So let's return to the correspondence between quantum and classical stat mech. And let's ask a similar family of questions. We're going to talk about microcanonical states in classical stat mech, which are just uniform probability distributions on some portion of phase space. So maybe we have some simple region in phase space. We think about a uniform probability distribution over that region, and that's going to be a classical microcanonical state. So we can talk about the entropy difference of two microcanonical states using the measures on phase space. And it is, as you would expect, exactly equal to the log of the ratio of the phase space volumes. Now, just as in our black hole case, the individual volumes are not defined, but the ratio is independent of our choice of measure on phase space. And the analogy to what we were just talking about in black holes is that any two simple phase space regions are related by some diff, but they can't be related by a symplectomorphism, something that preserves the structure of phase space, unless their volumes are the same. Let me help with a figure. So on the left, I've drawn two phase-space regions of different volumes. And they're simple regions, so I can always create some funky diffeomorphism that expands the smaller one to the bigger one, but it's not going to respect the fundamental structure of phase space. If I want to respect the fundamental structure of phase space, I need to consider regions that have the same phase space volume. And then, at least in this example, I can relate them by a simple translation. So this is exactly like what was happening in semiclassical quantum gravity. In order for two microcanonical states to have the same entropy, they must be related by a map that preserves the structure of the theory. In this case, those maps are symplectomorphisms. In the gravity case, they were isometries in our semiclassical algebra. But what's cool about this case is that we can actually see explicitly how this restriction, that we only compare volumes with a particular class of maps, arises from the underlying quantum theory. Okay, so I did this in two examples. One is the particle on a circle, the other is the harmonic oscillator. The harmonic oscillator is more non-trivial, so that's the one I'm going to present. What I did in this paper was I studied the classical limit of quantum information theory using the technology of Wigner functions. It doesn't matter if you know what these are. The point is that Wigner functions are a way of formulating quantum mechanics that explicitly uses phase space. They're useful because you can actually take h bar to 0 and use the same language all the way. You have quantum mechanics on phase space, you take h bar to 0, you end up with classical mechanics on phase space. And in reality, what actually happens at the mathematical level is that at finite h bar, if you have a density matrix, you rewrite it as something called a quasi-probability distribution on phase space. And in the classical limit, these things become true probability distributions. It's called a quasi-probability distribution because it's still some function on phase space that integrates to 1, but it can have negative regions. It doesn't have to be positive everywhere. Okay, so what you can do is you can study a microcanonical state for a simple harmonic oscillator. And what that means is you take some, just some family of states dependent on h bar that contain all of the energy eigenstates. They're uniformly mixed over all the energy eigenstates in a particular energy range. And what you can show is that you can compute the Wigner function of this thing and take the classical limit, and exactly what you expect happens, which is that it converges to a uniform probability distribution of phase space in a certain annulus, which gives you the right energy ranges. I should actually say that I was really shocked to learn that no one had done this computation in the literature, and it was actually kind of annoying to do. It's not like interesting, but you have to do a lot of special functions, asymptotics and things to show that this happens. This is one of those situations in physics where like, duh, this had to happen, but unfortunately you can't just say it has to happen. You have to do some calculation. Nevertheless, I'm sure you would have all believed me if I didn't tell you I did the calculation. And none of you are ever going to look at the calculation, so you're probably, I could have gotten away with murder anyway. Regardless, this is the microcanonical state of the harmonic oscillator in the classical limit. And indeed, the symplectomorphisms show up because if two annuli have the same phase space volume, then there is a symplectomorphism that relates them. And I've drawn it here. It's just a shift in the energy, but the energy is nonlinear in x and p. So this looks like some nonlinear transformation in x and p. What it does is it takes sort of small radius thick annuli and squashes them out into large radius thin annuli. Okay. So if and only if these microcanonical states have the same phase space volume, there is a symplectomorphism that relates them. So the question is, why did we have to compare these things using a symplectomorphism rather than a general diff? And the answer I want to offer you is that this symplectomorphism actually arises literally as the classical limit of an energy shift in the quantum theory. So in this example, there's another explicit calculation you can do, which shows that if you start with the quantum isometry that just shifts your energy levels, and you compute what it does in the classical limit, it reproduces exactly this symplectomorphism. Let me just say, what I mean when I say compute what it does in the classical limit is that you take this V, you see what it does to the position momentum operators, and then you take the h bar to 0 limit. And you find that while it does something very complicated to the position and momentum operators at finite h bar, in the h bar to 0 limit, it just gives you exactly this map. So the upshot of all of this
Are
is
those the only symplectomorphisms that exist? I mean,
a good question. Oh, sorry, the only symplectomorphisms that exist, or?
yeah, like, I mean, if you take this, if I take an annulus, can I move it to a completely different shape by a symplectomorphism?
Yes, well, it kind of depends. If you let yourself chop it up and then do different symplectomorphisms to different pieces, then absolutely, right? For example, at the classical level, I can map a single annulus to some sort of split thing, like this. That's kind of crazy. I don't know what this looks like at the quantum level or if it even has an analog at the quantum level.
Are you somehow restricting yourself to stationary states? That's the property that annuli have, but I could consider any blob of phase space anywhere you like.
Yeah.
And it'll just sit there orbiting phase space,
Absolutely.
but it's therefore, then it's not
So
stationary.
let me make the motivations very clear. I'm not making a claim about what happens in every single case. I'm just making a claim about what happens specifically to the microcanonical energy states of the simple harmonic oscillator. The microcanonical energy states are stationary. They become these annuli. Different annuli are related by symplectomorphisms, and those arise as classical limits of isometries in the quantum theory. Now, one thing that I think should be kind of obvious, at least intuitively, is that if I were to do something at the classical level that was not a symplectomorphism, I wouldn't expect to be able to get that from an isometry in the quantum theory, because it's just sort of too violent to the structure of the theory. I'm not making any claim about every symplectomorphism being realizable in the underlying theory. I'm saying at least these ones are, and I think things that aren't symplectomorphisms won't be. And this is what I think is happening in the information theory of the semiclassical limit of quantum gravity. The reason that we had to compare in the semiclassical limit, the reason we had to compare sort of amounts of information using these special gauge invariant operators is that other operators I don't think would show up as reasonable limits of the underlying theory of quantum gravity. I think we should take this very seriously as a paradigm for thinking about what parts of the underlying microscopic theory of quantum gravity we can still access in the semiclassical limit. These infinities can be accessed by moving things around with maps in the semiclassical limit that respect the underlying structure. I think that's a key insight, at least for me, in thinking about what is legal to do in the semiclassical limit if what I really want to study is quantum gravity. Okay, that's the full talk. Let me just end with a summary slide. I told you about this cross-product technology, recent developments that have created a bottom-up way to compute entropy differences in the semiclassical limit. I told you how we could use tools from operator theory to interpret these as counting a relative index of infinity by saying how much bigger one infinite rank microcanonical state is than another. I told you that I think everything about this construction should arise by taking a consistent limit of a theory of quantum gravity. But because I couldn't control any of this explicitly, I showed you that everything does work out in exactly the way I expected for understanding this analogy of classical and quantum stat. I think there's plenty of interesting stuff that one could do to try to do this more explicitly in a theory of quantum gravity. There's some two-dimensional theories of quantum gravity in which one might in principle have enough control to check a similar thing. But for me at least, I feel this is giving me some real insight into how much you can access purely at the semiclassical level and where it comes from in sort of the fuzzy soup of quantum gravity. That's all I have to say. Thank you.
There's a game sometimes people play in the classical theory in the presence of black holes, which is that you can take anything that you can construct classically, and if you shove it close enough to the horizon, it costs you no energy. And so you can pile lots of semi-classical configurations. They look like they have as low an energy as you want, and yet that's some excuse for the entropy being enormous. So what does your formalism say about things like that?
I don't know if my formalism says anything about that, because the formalism would be more about telling you how much the entropy changes if you already have shoved some stuff near the black hole and then you shove more near it. The fact that you can shove an enormous amount of stuff near the black hole as telling you that the entropy is, say, formally infinite in the classical limit
But your formalism doesn't provide a regularization of that entropy, is I guess what I'm asking.
No, okay. You could ask different people in my community and they would tell you different things. There are extremely ambitious people who will tell you that this technology will be upgraded to give you some good regulator for the infinite constant. I don't really think that's true. I think that what we're accessing is how much entropy changes. There's a reason I framed this as doing the classical stat mech of quantum gravity. I don't have any aspirations towards replacing string theory by doing this.
So in the case when you have spinning black holes with the same area, there should be an symplectromorphism in the classical phase physicists compared to the unspinning case.
No. So I was only talking, right, so the question is, I was talking about a specific sector of fluctuations around a fixed black hole, and I chose to only look at mass fluctuations. I could have chosen to also look at angular momentum fluctuations. No one's done this very carefully, so I don't know what happens. But I certainly wouldn't expect to be able to compare black holes with parameters that are different at order 1. Even if they have the same entropy, they're sort of fundamentally different backgrounds for the semiclassical theory. And
In the harmonic oscillator case, isn't that sort of happening? Like the energies being different would correspond to like black holes having different mass.
no, I think it's different. So it would be more like in the harmonic oscillator, for example, you could look at everything I was telling you was about the Hilbert space of that sort of describes fluctuations around the vacuum state of the harmonic oscillator. And, you know, well, in the harmonic oscillator, it's so simple that, okay. In continuum theories, there are often these things called sectors, which are different Hilbert spaces that describe different backgrounds. So for example, in spontaneous symmetry breaking in quantum field theory, you get different Hilbert spaces that describe different vevs for the fields.
Yeah.
Or even in ordinary scalar field theory, you have different Hilbert spaces defining thermal states at different temperatures. Semiclassical gravity in different backgrounds is like that, right? So the space of fluctuations around a black hole of a fixed mass is not related in perturbation theory to the space of fluctuations around black holes of a different fixed mass or different fixed charges. And all of this is just about perturbation theory. A similar thing doesn't really show up in the harmonic oscillator because it's a zero-dimensional system.
So those kinds of infinite, like those kinds of differences are not.
Those are even more infinite than, right? So the way you should think about this is that the formula, the Bekenstein-Hawking formula is like, oh God, it has an A over 4G in it, right? Okay, I guess I could have just said that without scrolling all the way back. Okay, Bekenstein-Hawking has an A over 4G in it. And what that means is that if you change the area only by order G, you expect the change to be finite, even in the limit where quantum gravity is completely turned off.
Yeah.
And that's what we're accessing. But if you change the area by an order 1 amount, or really if you change any of the parameters of the black hole by an order 1 amount.
But I can change the parameters and.
No,
keep the
I know
area.
what you have in mind, right? You're saying, oh, make it so that it's still only an order G Newton change in area, but the macroscopic parameters are very different,
Yeah,
right?
that sounds legal.
In principle, it sort of looks like this formula can accommodate it. I
Yeah.
would say the formalism can't accommodate it, but maybe I'm wrong. I mean, I don't know. I think that, well, I'd have to think to cook up some quantum mechanics example to explain why I don't think that can happen, but
But
if
it
it could
can
happen, that
I
would be
just
great.
was asking whether that's possible or not, but.
I think that probably because this is all perturbation theory around a fixed background, I think the formalism can't accommodate that. Although I agree that the entropy formula sort of makes it look like it could.
Thank you.
Any other questions?
Something simple that confuses me. You said in the beginning that all this stuff you can do in gravity, but you cannot do in quantum field theory. But in some situations, those two are related by holography. So whatever it is that you can do here, you can just translate it to the other language.
Good.
What does it correspond to there?
So the reason for this is that, okay, So let me think of the best way to say this. So think about the thermal field double state in holography. So maybe I want to make a new, just want to draw something. Okay. Let's think about the thermal field double state in holography. So in the bulk, it's like an eternal Schwarzschild black hole. And in the boundary, it looks like an entangled state on two cylinders. So the thing that's happening here is that in the bulk, just bulk quantum field theory, you have problems talking about entropy because this region has UV divergences at the bifurcation surface. And those go away when you couple the bulk quantum field theory to gravity. On the boundary side, the portion of the boundary just quantum field theory that's dual to this region is a complete cylinder that doesn't have any UV divergences. So if I'm talking about the entropy associated with sort of a complete region or a complete asymptotic boundary of the dual quantum field theory, then I don't have these issues with UV divergences. And this is quite similar to what happens in the bulk, where you naively have UV divergences, but the inclusion of gravity regulates them. Maybe that, I don't know if that answered your question.
Not sure, maybe I'll ask you later.
Maybe what I'll just say is that when I said that I couldn't do this in quantum field theory, what I meant was that I couldn't do this for subregions in quantum field theory. But for mixed states on like a full quantum field theory spacetime, which are the kinds of things that show up when you're describing black holes in holography, I can do this kind of thing just in quantum field theory, because there are no UV divergences.
Any other questions? No, let's thank John again.